Good morning. So let us first recall the formulas that we saw yesterday. So the velocity of electron in nth Bohr orbit of an alkali atom is given by this formula. It is z times e square divided by 2 epsilon naught hn, right? So this formula is rarely used, but still we need to remember this. And here, looking at this formula, you can get an idea that Vn is directly proportional to what? Z by n. It's proportional to Z by n. Okay, so Z is the atomic number of alkali atom and n is the principal quantum number. Okay, or you can simply say it's the orbit number. And then if you substitute the values of these things, okay, if you just substitute values of these things, then you can rewrite this formula in simple form like this: Vn is equal to alpha times Cz by n. Okay, so this is a simple formula. Just remember this: Vn is equal to alpha times Cz by n. What is alpha? Alpha is called as fine structure constant and its value is 1 by 137. Okay, so then this is very simple formula. Vn is equal to alpha times Cz divided by n, right? Then we also saw that energy of electron, the radius of electron in the nth Bohr orbit of an alkali atom is equal to epsilon naught h square n square divided by pi m e square times z. Okay, epsilon naught h square n square divided by pi m e square times z, right? So then here you need to remember this formula too. Then if you put z equal to 1, n equal to 1, you get, and substitute all other values, this thing, epsilon naught h, etc., mass of electron, then charge on electron, then you get the radius of first Bohr orbit of the hydrogen atom. Why hydrogen atom? Because we have put z equals to 1. Z equals to 1 means atomic number is 1, so this is hydrogen atom. Okay, so you get energy of the first orbit of the hydrogen atom, right? And this is called as Bohr radius. Bohr radius is equal to a naught, that is 0.5 angstrom unit, 0.5 angstrom unit. Okay, and then now if you substitute this back in this formula, so these things, the value of these things is equal to a naught. What remains is a naught times n square by z. Okay, so you get Rn is equal to a naught times n square by z. Okay, so this is the radius of electron in nth orbit of an atom, alkali atom having atomic number z, right? If you want it for hydrogen atom only, it's just equal to what? Rn is just equal to a naught times n square. Okay, good. Then we saw another formula, that energy of electron is given by this formula, that is minus RCH z square by n square. Okay, minus RCH z square by n square. And if you substitute the values of RCH, that is minus 13.6 electron volts. Okay, and that is energy of electron in first Bohr orbit of hydrogen atom, right? So En, so what we'll do is we'll write here Enz. Let's write this thing as Enz, and this thing also as Rn suffix z. So this is energy of electron in nth level of an alkali atom having atomic number equal to z, and this is radius of electron in nth orbit of alkali atom having atomic number equal to z, right? So then Enz is equal to, what do you get? You get E1, this is energy of electron in the first orbit of hydrogen atom, that would be equal to minus of RCH, and its value is equal to minus 13.6 electron volts. So it is E1 times Enz is equal to E1 times z square by n square. Okay, and the formula for this Enz, the exact formula is minus me to the power 4 divided by 8 epsilon naught h square times z square by n square, right? So this is a complicated formula. Remember this one also, but this formula and this one is extremely important, right? So as we said, ENZ is equal to what? ENZ is equal to minus of RCH Z square by N square, okay? And if you want it for hydrogen atom, then put Z equals to 1. What do you get? En is equal to minus of RCH by N square, okay? And if you put n equals to 1, what do you get? You get E1. E1 is equal to minus 13.6 electron volts, okay? So what would be energy of nth orbit? Energy of nth orbit is just equal to minus of RCH. Its value is 13.6 electron volts. 13.6 electron volts, right? So En is just equal to E1 divided by N square. You get E1 divided by N square, and E1 is equal to what? It is minus of 13.6 electron volts, right? Actually, we have written it here, over here, that En is just equal to minus 13.6 electron volts divided by N square, or it is E1 divided by N square, okay? So we had seen these formulas yesterday. Then it's better to remember the energies of first 4 orbits of hydrogen atom. So energy of the first orbit is minus 13.6 electron volts. Energy of second one is minus 3.4 electron volts. Energy of third orbit is minus 1.5 electron volts, and energy of the fourth orbit is minus 0.85 electron volts, okay? We can calculate it, but it's better if we remember these 4 values at least, right? Because we'll need not spend any time in calculations, okay? All right, so then next is the frequency of radiation. So we know this from the Bohr's theory, that when electron jumps from a higher orbit to lower orbit, so suppose electron revolves in this initial orbit, this is initial orbit I, and then it jumps from this initial to final orbit, okay, I to F, let's say, initial to final, okay? So electron has jumped from here to here. What happens? It emits a photon. When electron jumps from this higher to lower orbit, it emits a photon, and the energy of that photon, h nu, would be just equal to the energy difference between these two orbits, right? It is just equal to energy of this initial orbit, EI, minus energy of the final orbit, EF, right? EI minus EF is equal to h nu. Then we can make use of the formula, this formula, that energy of nth orbit of electron in an alkali atom having atomic number Z is minus of RCH Z square by N square. Using that, what do you get? You get, see, H will be here also, so it is minus of RCH, that H and H on this side gets cancelled out, so you get minus of Z square RC times 1 by N square, but it will be 1 by Ni square. Ni means it is the nth level, okay, nth initial level, right? Ni, nth initial level, to the electron jumps from Ni, okay, level Ni to Nf, okay, right? So then you have minus Z square times Rc, 1 by Ni square minus 1 by Nf square, okay? This thing is taken common. So after that, now this nu can be written as Z square times Rc, 1 by Nf square minus Ni square. This minus sign, negative sign, is absorbed in the bracket, and after that you can write nu is equal to what? It is C by lambda. If you use that, C and this C gets cancelled out. So 1 by lambda is equal to Z square times R times 1 by Nf square minus 1 by Ni square. You need to remember this formula, okay? So we had seen similar formula for hydrogen atom only, okay? This is formula which is applicable to any alkali atom, okay? What's the difference? So we just have this Z square in multiplication with this term for the hydrogen atom, right? So if you want the wavelength of a photon when electron jumps in hydrogen atom from, let's say, the initial level Ni to final level Nf. Then what's that wavelength? 1 by lambda, put z equals to 1, r times 1 by Nf square minus 1 by Ni square. Okay, 1 by lambda, put z equals to 1, r times 1 by Nf square minus 1 by Ni square. So that's simple. Okay, and then finally let's see drawbacks of Bohr's atomic model, and after that we'll solve some problems. Okay, so Bohr's model is not applicable to all atoms. So it's applicable to hydrogen atom and hydrogen-like atoms, hydrogen-like alkali atoms. Okay, Bohr's model is applicable to only hydrogen atom and hydrogen-like alkali atoms only, which have one electron in the outermost orbit. Okay, Bohr's model doesn't explain intensity of emission spectra. It explains emission spectra, the origin of spectra, that when electron jumps from higher to lower orbit, it emits a photon. Okay, that is spectra, but it does not explain the intensity. So frequency of the intensity of which frequency or which spectra would be how much, it is not explained by the Bohr's model, right? And it doesn't give any reason for quantization of angular momentum. So we had seen that angular momentum of electron in the nth orbit, it's equal to what? Nh by 2 pi. This is called as quantization of angular momentum because it comes in fixed quantity. What quantity? N times h by 2 pi, right? But then he didn't give any reason for that. So let's see the reason. So actually de Broglie was the person who explained the quantization of angular momentum using his hypothesis, de Broglie hypothesis. Okay, so what is de Broglie hypothesis? De Broglie says that just like there is dual nature of radiation, there is dual nature of matter also. Okay, he says that suppose there is a particle moving with velocity v, its momentum p is equal to what? M times v. Then this particle behaves like wave also. Okay, that's the dual nature. And what will be wavelength of that wave? So lambda is equal to h by p, Planck's constant divided by p. Okay, p is the momentum, right? Lambda is equal to h by p. This is de Broglie's hypothesis. Now what's the connection here? So see, we had seen stationary waves. What happens in the stationary waves? So suppose you pluck a string which is tied between two rigid supports, okay, two walls suppose, then all kinds of wavelengths will be generated. There will be all kinds of waves generated, right? But then the waves travel from this end to that end, from that end to this end. So only a few waves can survive. Okay, so wave going from here to here and coming back, these are the waves traveling in opposite direction. So they form a stationary waves and the string vibrates forming loops. Okay, so we had seen this in stationary waves. So string vibrates forming a loop, right? So what is the wavelength of what's the connection between this length or the distance covered in round trip? What is distance covered in round trip? So the wave goes from here to here and it comes back. That is the distance covered in round trip. So that is equal to what? It would be equal to either lambda, because one loop has length equal to what? Lambda by 2, right? This is a crust and trough. This much distance is lambda. So how much would be this distance? From here to here only, it is lambda by 2. So then wave goes from here to here, then it comes back. So total distance would be lambda by 2 plus lambda by 2 means lambda, right? Okay, yes, no? All right, good. So the distance covered would be either lambda, or if two loops are formed, the distance covered in round trip is 2 lambda, or if three loops are formed, then distance covered in round trip would be 3 lambda, so on and so forth. Okay, so distance covered by a wave which is trapped between two rigid supports is equal to what? It's equal to n times of lambda, distance covered in round trip. Okay, then here de Broglie says that since electron is bound in an orbit, it should be thought as a stationary wave or standing wave, not like a traveling wave, because it is trapped in a orbit. Okay, so it moves in the orbit again and again. It's like this wave is moving in this orbit, right, from here to here, and it comes back again and again. Okay, then electron should be thought as a standing wave or a stationary wave. And then therefore how much is distance covered in a round trip by electron? So it is equal to length of the orbit, right? So distance covered in a round trip is equal to length of the orbit, that is 2 pi times r suffix n, 2 pi times r, but rn, why rn? Because it is radius of nth orbit. So distance covered in round trip must be equals to what? N times of lambda. We have seen this for stationary waves, so it is true for stationary waves due for the motion of electron also. Okay, so electron behaves here like stationary waves, that is the point. So 2 pi rn is equal to, you have n times lambda, and wavelength of matter waves is given by de Broglie hypothesis. So what is de Broglie hypothesis? Lambda is equal to h by p, right? So therefore you have lambda equals to h divided by m times v, and we are taking vn because it's nth orbit, so speed is equal to vn, right? So put that here, so you get 2 pi rn is equal to nh divided by m times vn, and move that m times vn on this side, 2 pi on the other side, so 2 pi goes in denominator, so you get m times vn into rn. So mvr, this is the angular momentum, right? This is angular momentum, and it's equal to nh by 2 pi. Okay, it is equal to nh by 2 pi. So this explains the quantization of angular momentum, right? This explains the quantization of angular momentum. Okay, is this thing clear? All right, good. So then now let us solve some problems based upon all these things. Let's see this one. The wavelength of first line of Lyman series for hydrogen atom is equal to that of the second line of Balmer series for hydrogen like atom. Okay, the atomic number Z of this hydrogen like atom is, so they say that the wavelength of first line of Lyman series, okay, first line of Lyman series, first line of Lyman of hydrogen is equal to what? It's equal to second line of Balmer of some atom having atomic number equal to Z. Okay, so then what is first line of Lyman series? So it is r multiplied by 1 by 1 square minus 1 by 2 square, right? This is Lyman series, that means final orbit is first orbit only. Okay, our formula is 1 by lambda is equal to r multiplied by 1 by nf square minus 1 by ni square. So this is for hydrogen, and for alkali atoms, what's there? There is just z square in multiplication with this r. And if it is Lyman, then nf is equal to 1. If it is Balmer, then nf would be equal to 2, right? So this is second line of Balmer series of an atom having atomic number z. So that is equal to r times z square multiplied by 1 by, because this is Balmer series, so final orbit is second orbit. Okay, 1 by 2 square minus 1 by, and we want second line. If it was first line, then it would be 3 square. Because it's second line, so we have 4 square, right? So r gets cancelled out, then there is nothing. This is very simple. This is 1 minus 1 by 4, so that's 3 by 4. Okay, so 3 by 4 is equal to z square times 1 by 2 square, so this is 1 by 4 minus 1 by 16. Okay, so 1 by 4 means 4 by 16. Okay, 4 by 16 minus 1 by 16 is how much? This is 1 by 4, means it's 4 by 16 right? 4 by 16 minus 1 by 16 is 3 by 16. So z square times 3 by 16. So again 3 gets cancelled out, okay, and we can take this 16 on this side. 16 by 4 gives us 4. So from that we get z square is equal to 4 and therefore z is equal to 2, right? So it is option D. Okay, this is clear. Simple, right? Okay, good. Let's see next one. Consider third orbit of He, helium, using helium plus, okay. Using non-relativistic approach, the speed of electron in this orbit will be, okay, what is the speed of electron? So what's the formula? Okay, so Vn is equal to alpha times Cz divided by n. This is the formula, right? So let's just substitute values. So alpha is 1 by 137 multiplied by C is 6 into 10 raised to E is 3 into 10 raised to 8. Okay, what is Z? This is helium. So Z is equal to what? Z is equal to 2, and then you have N. So which orbit? Third orbit. So N is equal to 3. Okay. So then we just need to solve this. So this is 2 by 137 multiplied by 10 raised to 8. 2 by 137 into 10 raised to 8. So this thing would be nearly equal to what? 10 raised to 6, 10 raised to 6 is there. So let's take 2 divided by 1.37 multiplied by 10 raised to 2, and this is 10 raised to 8. So 10 raised to 8 divided by 10 raised to 2 is 10 raised to 6, right? 2 by 1.37 is how much? 1 point something, okay, 1.4 something into 10 raised to 6, right? So it should be option D, I guess. 1.46 multiplied by 10 raised to 6 meters per second. Okay, this one is clear. It's a direct formula, right? Alpha times Cz divided by n. Okay, okay. So monochromatic radiation emitted when electron on hydrogen atom jumps from first excited state to ground state irradiates a photosensitive material. Okay, so monochromatic radiation emitted when electron in an hydrogen atom jumps from first excited state to the ground state, means second state to ground state, irradiates a photosensitive material. Okay, so this is hydrogen atom, electron jumps from here to here, right? It's like this is hydrogen atom and electron jumps from the second orbit to first orbit, okay, and it emits a photon of energy equal to what? H nu would be equal to E2 minus E1, right? E2 minus E1. Okay, so then H nu equals to E2 minus E1. Then after that the stopping potential is measured to be 3.57 volts. So what happens? This electron strikes on the photosensitive material. So it's this, sorry, did I say electron? This photon strikes on the photosensitive material, and due to that an electron will be emitted. To stop that electron, you need stopping potential of 3.57 volts. The threshold frequency of the material is. So tell me what to do. First of all, find out the energy of this one. Right, find out the energy of this one. So energy of emitted photon, would be just equal to what? E is E2 minus E1, because it's electron jumps from second to first orbit, then this photon is emitted. So E2 is E1 by 2 square E1 by 4, right? And E1 is equal to what? E1 is minus 13.6 electron volts. Okay, it would be better if you remember E2 is just equal to minus 3.4 electron volts, right? So this is minus 3.4 minus 13.6 electron volts, and how much is this? So I guess this is plus 13.6, right? Minus minus plus. So 13.6 minus 3.4 is 10.2 electron volts, right? So this is E, energy of this photon, this emitted photon, and then this is energy of this emitted photon. Then it strikes with this photosensitive material, so stopping potential is 3.57 volts. So you know the stopping potential is V naught. Okay, if stopping potential is V naught, then you have E times V naught is equal to h nu, or energy of this photon, right, minus the work function. Okay, so h nu, or let's say E minus phi naught. Let's substitute the values. So this is what? Stopping potential is 3.57. 3.57 is equal to E is 10.2 minus phi naught, and from that you get phi naught is equal to what? 10.2 minus 3.57 minus 3.57. So how much is that? 10.2 minus 3.57 is 6 point something, 6.43, and plus this 2.2, so 6.63. Is it correct? 6.63, right? Yes, no, this is correct. Check my calculation. Okay, good. So now what do you want is the frequency, the threshold frequency of this material. So this is this stopping potential, sorry, this work function is in terms of electron volts, and then you want threshold frequency. So that is, you can write this as h times nu 0 is equal to 6.63 electron volts, right? Then now we need to find out the nu naught. Let's find out nu naught. Okay, I guess better thing to do is I will just multiply it by C. No, but that will give me okay, so just take, yeah, so h is, what is h? It's 6.63 multiplied by 10 raised to minus 34 times nu naught is 6.63 electron volts. So electron volts means it is 1.6 into 10 raised to minus 19 joules, right? So just multiply this with charge on electron, so you get answer in joules. So then this thing gets cancelled out. Okay, this is 6.64, but right, roughly we can write it as 6.63. So then this thing gets cancelled out, right? And take this 10 raised to minus 34 on that side, so it becomes 10 raised to plus 34. So you get nu naught therefore is equal to 1.6 multiplied by 10 raised to plus 34 minus 19. So 34 minus 19, how much is this? 34 minus 19 would be 15. Yeah, 15. 10 raised to 15 hertz. This should be the answer. 1.6 times 10 raised to 15 hertz. Option C. Okay, this is clear, right? Yamini, this is clear? Okay, good. Let's see next one. An electron in the hydrogen atom jumps from excited state N to ground state. The wavelength, so emitted illuminates a photosensitive material having work function of 2.75 electron volts. If the stopping potential of the photoelectron is 10 volts, then the value of N is. So what's happening here? Again, it's similar question. An electron in hydrogen atom jumps from excited state N to the ground state. Okay, excited state N to the ground state, right? So then electron jumps from excited state N to ground state. So this is state N. So here it will have energy En to the ground state. Here it will have energy E1, and it radiates a photon having energy equal to what? H nu, which would be equal to En minus E1. Okay, so energy of photon E is equal to what? En minus E1. Alright, so then you know what is En? En is just E1 divided by N square. Okay, E1 divided by N square, right? And the wavelength, so emitted illuminates a photosensitive material. So this emitted photon strikes with a photosensitive material having work function equals to 2.75 electron volts. So work function of that material is 2.75 electron volts. If the stopping potential of the photoelectron is 10 volts, stopping potential is 10 volts, then the value of N is, what is N? Okay, this is the question. All right, so then you can take E1 common from here. Okay, so what remains is 1 by N square minus 1, right? So now this, okay, this photon strikes with a photosensitive material, and for that we can write Einstein's photoelectric equation, that E times V naught would be equal to what? E minus phi 0, right? Then therefore you have, okay, put V naught. How much is V naught? So stopping potential is 10 volts, so it's E times 10 volts is equal to E minus phi naught. What is phi naught? Phi naught is 2.75, okay, electron volts. This is in electron volts, so this is E times 10 volts, right? So that means energy is 10 electron volts. So take this 2.75 on this side, so you get E equals to 10 plus 2.75 means 12.75 electron volts, and that is equal to what? E1. Okay, E1 multiplied by 1 by N square minus 1, and what is E1? So it's minus 13.6 electron volts, so that's equal to 12.75. all right, so then you need to solve this, right? So take this 13.6 on that side, so this is 12.75 divided by 13.6, that would be equal to minus of 1 by N square minus 1. Okay, or you can absorb that negative sign inside, so it will be 1 minus 1 by N square. 1 minus 1 by N square is equal to what? Take this 13.6 on that side, so it goes in denominator, 13.6, right? So this thing would be nearly equal to what? 0.9 or something, I guess. So 1 minus 1 by N square is equal to this one. Okay, so what we can do is we can move this minus 1 by N square on that side, this thing on this side. All right, so we have therefore 1 by N square is equal to 1 minus 12.75 divided by 13.6, right? And then let's multiply and divide. we got this. Then this is 13.6 minus 12.75 divided by 13.6, that's equal to 1 by n square. How much is this 13.6 minus 12.75? 13.6 minus 12.75. Okay, it is 0. What, 0.85 or something. 13.6 minus 12.75. So this thing would be 5. Okay, 5, 7, 15 minus 7 is 8. Then right, 0.85. It is 0.85. So it's 0.85 divided by 13.6. Okay, 0.85 divided by 13.6. So this is 1 by n square, right? So now if you divide this 13.6 by 0.85, what will you get? You will get a number which is little bit greater than 13.6. Okay, so you can say it will be close to 16, right? Because this is 1 by n square, and the principal quantum number would be what? It would be 1, 2, 3, 4, something like that. Okay, this is 1 by n square. That means this number must be close to what? Some square. So 13.6 divided by 0.85 will give you near about 16. Okay, and therefore this is equal to what? N square is equal to 16, right? And therefore n would be equal to what? N is equal to 4. So I guess that's the answer. N is equal to 4. So it's option C. Okay, is this thing clear, everyone? The energy of a hydrogen atom in a ground state is minus 13.6 electron volts. The energy of He ion in the first excited state will be. So energy of hydrogen atom in the ground state is minus 13.6 electron volts. The energy of He plus ion in the first excited state will be, right? So you want energy of this ion in the first excited state. So what's the formula for energy? Energy of an alkali atom is equal to what? It is Z square by N square times of E1 of energy of hydrogen atom, right? Okay, so you want it for the first excited state. Okay, you want it for the first excited state. So that means N is equal to 2, and this is He plus. So for He plus you have Z equals to 2, right? So it is 2 square by 2 square times E1. Okay, let's put suffix EZN here. So what does it mean? Energy of alkali atom having atomic number equal to Z, and it is energy of electron in nth orbit. Okay, principal quantum number is n, right? So it is Z square by n square times E1. Okay, we know that. So Z is equal to 2, n is also equal to 2, and that's why this thing gets cancelled out. And then you have E1. E1 is what? It's minus 13.6 electron volts, and therefore the answer is just minus 13.6 electron volts. Okay, so this was one of the simplest question till now. This is clear? Okay, so here En is equal to minus of RCH Z square by n square. Okay, this is the formula. So it's directly proportional to Z square, inversely proportional to n square, and if you put Z equal to 1, n equal to 1, what do you get? You get energy of hydrogen atom, okay, of first orbit, right? Energy of hydrogen atom for the first orbit, and that would be just equal to minus of RCH, which is minus 13.6 electron volts, right? Okay, good. So this thing is just E1, so that's why your formula En is equal to what? E1 times, or we can write it over here that En is equal to it's just equal to E1 times of Z square by N square. Okay. Alright, let's see next one. The electron in hydrogen atom jumps from excited state n equal to 3 to its ground state n equal to 1. The electron in hydrogen atom jumps from excited state n equal to 3 to its ground state n equal to 1, and the photons thus emitted irradiate a photosensitive material. Oh, this is similar. If work function of the material is 5.1 electron volt, the stopping potential is estimated to be, work function is given and you want stopping potential. So it jumps from n equal to 3 to n equal to 1. So just find out the energy of the emitted photon, right? So energy of emitted photon would be equal to E3 minus E1, and that is minus 13.6 divided by what? 3 square. This is E3, okay, minus 13.6. So here we need to be careful. This is minus of minus, right? So we shouldn't write minus directly 13.6 here. Okay, so then it is what? So minus 13.6 divided by 3 square. So E1 is minus 13.6, E2 is minus 3.4, E3 is minus 1.5, and E4 is minus 0.85. Okay, so just remember that, it will save you some calculation, because most of the times first, second, third, fourth orbits are involved. Okay. So the question, okay, so this is equal to energy of the third orbit is minus 1.5 electron volts. Then you have plus 13.6. So minus 1.5 plus 13.6 is what? 13.6 minus 1.5 is 12.1. Okay, 12.1 electron volts. So you got energy of the emitted photon. Then the stopping potential, you want to find out stopping potential. The work function is given, you want to find out stopping potential. So this is simple. So you have this formula, E V naught is equal to what? H nu, or energy of the photon, E minus phi naught. Phi naught is given, it's 5.1. You just substitute that. This is 12.1 minus 5.1 means 7 electron volts. This is E times V naught, and that's why what would be V naught? V naught is just 7 volts. That's the answer. It's option D. Okay, this is clear. Right? Yes, no? Okay, it's simple. Good. Let's see next one. The ground state energy of hydrogen atom is minus 13.6 electron volts when its electron is in first excited state. Its excitation energy is. Now what is excitation energy? So first of all, find out the energy of that orbit. Okay, so it is first excited state, means it's E2. E2 is equal to minus 13.6 divided by 2 square. Okay, and I asked you to remember the energy of first 4 orbits. So this is minus 3.4 electron volts. Now this electron has energy equals to minus 3.4. okay, it's in second orbit and its energy is equal to minus 3.4 electron volts, right? Now suppose you want to make it free. Okay, how much of energy is needed? So energy needed would be equal to what? Plus 3.4, and that is called as the excitation energy. Okay, that is known as the excitation energy. So what is the excitation energy then? It's plus 3.4 electron volts, right? This is clear. Yes, no, tell me. Okay, good. All right, so this is excitation energy. if they ask the excitation energy required to excite it to the third orbit, then that would be equal to what? E3 minus E2, E3 minus E2. But if they say just excitation energy, what does that mean? It means you want to make the electron free. Okay, so you want to create ion of that atom, right? So whatever is negative energy here, just give that much of energy so that total energy would be equal to 0, and that means the electron is free. Okay, all right, let's see next one. The total energy of electron in ground state of hydrogen atom is minus 13.6 electron volts. The kinetic energy of electron in the first excited state is, okay, so what is total energy in first excited state? First excited state means the second state, right? So E2 is equal to, minus 13.6 divided by 2 square, that is minus 3.4. Just remember this, E2 is minus 3.4 electron volts, right? So this is energy of electron in the first excited state or second orbit or second state, right? So then we have relation between this total energy or energy and potential energy and kinetic energy. So we know energy is equal to what? Just minus of negative of the kinetic energy, okay, and it is just equal to the potential energy divided by 2. So we need to remember these equations forever. Okay, what is kinetic energy? So it would be equal to negative of the total energy in that orbit, in that state. Okay, so that is equal to what? Minus of this thing, E2, so plus 3.4. This is very simple question, right? Okay, everyone. All right, good. Let's see next one. The total energy of electron in the first excited state of atom is about minus 3.4 electron volts. Its kinetic energy in this state is, so this is repeated question. This is from 2005, this is from 2007. So what would be the kinetic energy? Just negative of this, negative of the total energy. So that is plus 3.4 electron volts. Okay, so that's simple. Let's see next one. In which of the following systems will the radius of first orbit be minimum? Okay, radius of first orbit will be minimum in these ones. Okay, which one of these? Tell me. Doubly ionized lithium, singly ionized helium, deuterium, and hydrogen atom. So what is the formula for the radius? Formula for radius of the atom having atomic number Z, right? Alkali atom. Okay, alkali atom having atomic number Z in nth orbit, but we want n equals to 1. So this is just a naught times n square by Z. This is our formula, right? It's a naught times n square by Z. Okay, so this is our formula, a naught times n square by Z. N is equal to 1, that means radius is just inversely proportional to Z. Radius is just inversely proportional to Z. A naught is a constant. A naught is 0.5 angstrom. So option A. Okay, so out of these, which one has the highest atomic number? Lithium, right? What's the atomic number of lithium? 3. Okay. Alright. So then the answer would be doubly ionized lithium. This is clear? Yes, no? Okay, good. Let's see next one. The energy of hydrogen in nth orbit is En. Then the energy in nth orbit of singly ionized helium atom will be. Okay, so again we have the formula. What energy of an atom, of electron in an atom having atomic number Z and its principal quantum number is n, means orbit number is n, right? So it's equal to energy of hydrogen atom in the first Bohr orbit multiplied by n square by z square. What's the formula of energy? Me to the power 4 multiplied by 8 pi epsilon naught h square n square, right? So z square is in numerator, n square is in denominator. Okay, so E1 times z square by n square. Okay, so then energy in nth orbit of singly ionized helium atom will be, right? Tell me. So for hydrogen it would be E1 divided by n square, and because they are asking about the helium, so this is energy of nth orbit of hydrogen, Hz n is E1 divided by n square, okay, times z square. Ezn is just energy of hydrogen atom in nth orbit times z square. Okay, what's the answer? It's 4 times En, right? It is just 4 times En. Okay, this is clear. Yes, no, tell me. Right, we have used this formula. En is equal to what? E1 times z square by n square. Okay, good. So then all right, so then the energy of ground state electronic state of hydrogen atom is minus 13.6 electron volts. The energy of first excited state will be, this thing you need to remember. First excited state means what? It's the second state, so the energy is minus 3.4 electron volts. Now if you remember this, then some questions will have direct answers, right? Okay, within a fraction of a second you can click the answer. Okay, let's see next one. When hydrogen atom is in first excited level, its radius is of the Bohr radius. So we know radius is what? R is equal to a naught times n square for nth orbit, or Rn is a naught times n square. Okay, so that is Bohr radius is a naught. So n is equal to 2. First excited level means n is equal to 2. So this is nothing. So 2 square, right? It's 2 square times a naught. That means 4 times of a naught. So it is option B. That's very simple. Okay, let's see next one. According to Bohr's principle, the relation between principal quantum number n and the radius of orbit r is. So radius is directly proportional to n square. We know that. Okay, so it's option D, right? All right, let's see this one. Hydrogen atom in ground state is excited by monochromatic radiation of lambda equals to 975 angstrom. Number of spectral lines in the resulting spectrum emitted will be. Okay, so first of all, just find out where does it go. Okay, so it's in ground state and you are giving energy equals to hc by lambda, right? So it's like your electron is revolving in ground state. Okay, and then this is the electron. Now a photon strikes with this electron. Okay, a photon strikes with this electron. So it goes from this ground state to some nth state. Okay, so suppose it goes till here, nth state. okay, E1 to, sorry, ground state to NH state. That means energy of the photon must be equal to what? En minus E1. So En minus E1 is equal to energy of photon, right? So En is therefore equal to E1 plus energy of photon. And what is energy of photon? H nu, but this is given in terms of lambda, so Hc by lambda. Then put the values. So this is minus 13.6 electron volts, okay, and then this is Hc by lambda is plus Hc is 12,000. This is given in nanometers, so let's write Hc equals to 12,400 nanometers divided by, you have 975, okay. So 975, so nearly 1000. So this thing would be equal to what? 1 point, we need to solve this unfortunately, right? 12400 divided by 975. So it is 12400 divided by 975 is 12.71, okay. So minus 13.6 plus 12.71. So this thing is 12.71, and if you solve this thing minus this thing, so then what you get is minus, sorry, yeah, minus 0.89, okay, minus 0.89. So this is En, nth orbit, energy of nth orbit is minus 0.89. So which orbit is this one? This is fourth one, right? Okay, this is fourth one. E1 is minus 13.6, E2 is equal to what? Minus 3.4, E3 is equal to minus 1.5, and E4 is equal to minus 0.89, right? Minus 0.85, sorry, not 9, it's minus 0.85, okay. So this would be fourth orbit. So this is near about what? Fourth orbit, because energy of fourth orbit, you know, it is minus 0.85 electron volts, okay. So then now it goes to the fourth orbit. Now how many spectral lines will it emit? This is the question, okay. How many spectral lines does it emit? This is the question, tell me. So answer to that is, you need to remember one formula, okay. So number of spectral lines emitted, number of spectral lines emitted just equal to n times n minus 1 divided by 2, okay. N times n minus 1 divided by 2, so it is 4 times 4 minus 1 is 3, right, divided by 2, right. So 4 by 2 is 2, 2 times 3 is 6, so it will emit 6 spectral lines, okay. For this question we can solve it, but generally you remember this formula, it is n times n minus 1 divided by 2, okay. So see, our atom is in fourth state, atom is in fourth state, then from fourth, where can it go? This is 4 3 2 1, so atom is in fourth state, it can go from fourth to directly first orbit, or it can go to the second orbit, right, or it can go to third orbit directly, okay. So how many spectral lines will it emit? Meaning how many photons can it emit from when it jumps from fourth to some state? 3 photons, okay, 3 different spectral lines, right. So then when it goes to third level, okay, when it goes to fourth, or from fourth to third, from there it can jump to the second and first, right? From there it can jump to second and first, like this. So this is 3 plus 2, 5 spectral lines. And when it goes to second, okay, when it goes to the second state, it can jump to the first state, like this. So 3 plus 2 plus 1, that means 6 spectral lines. Okay, is this thing clear, everyone? Okay, so now this was fourth orbit only. Okay, so electron is just excited to fourth orbit, so from there it can de-excite to the third, second, one, and number of spectral lines we can count by hand, but then it can jump to very higher orbit like 12th or 15th. Okay, you might get the value En. So what should you do? Just make use of this formula. It is n times n minus 1 divided by 2, right? Number of spectral lines emitted just equal to what? The orbit in which the electron is right now, that's nth orbit. Okay, so n times n minus 1 divided by 2, this is the formula. Just remember that. Okay, good. Then let's see next one. An electron of a stationary hydrogen atom passes from fifth energy level to the ground level. So electron goes from the fifth level to ground level. The velocity that the atom acquired as a result of photon emission will be. So electron goes from the fifth level to ground level. Okay, from fifth level to ground level. Let's say whatever level. Okay, so this is nth level. So electron goes from here to here, right? It emits a photon. So as a result of this, it is emitting a photon, right? As a result of this, what will happen? So if photon goes in this direction, the atom will move in the other direction. Just like you have a loaded gun and you fire a bullet. Bullet moves in forward direction, gun moves in backward direction, right? By the law of conservation of momentum. Okay, so initial momentum of this atom was 0. Let's suppose the atom was at rest. So then what would be the final momentum? So because this photon is moving, okay, photon is removed from the atom, it moves in this direction, so atom will move in other direction. It will get a recoil, right? It's recoil velocity. So the velocity that atom acquired as a result of photon emission will be. So this is simple. See, you can find out the energy of this photon, right? Energy of photon h nu would be equal to what? H nu is equal to E5 minus E1, because it goes from the fifth energy level to the ground level, right? And then you know the formula for energy. So it is E is equal to what? RCH divided by n square. Actually minus of RCH divided by n square. Okay, for hydrogen atom it is this formula. For some other atom it would be equal to what? Minus RCH by n square times z square. Okay, so for fifth orbit it will be equal to minus of RCH divided by 5 square, and minus minus plus, you have just RCH, right? E1 is just equal to what? Minus RCH. Okay, E1 is minus RCH. This minus minus becomes plus. This is divided by 25 RCH. Okay, so you have H nu equals to RCH divided by, this is, you can say 25 by 25, and this is minus 1 by 25, so that is 25 by 25 minus 1 by 25 is 24 by 25. Okay, 24 by 25 times of RCH. But then you want the momentum. Okay, you want the momentum, so find out momentum of this photon. This is energy of photon. What would be momentum of this photon? So you know momentum is given by de Broglie's relation. P is equal to what? H by lambda. So can you adjust H by lambda here? Yes, we can adjust, because we have nu which can be written as C by lambda. Right, nu can be written as C by lambda. So therefore we have Hc by lambda is equal to 24 by 25 times RCH. Cc gets cancelled. Okay, and H by lambda is P, momentum of photon. So momentum of photon P is just equal to what? R times H times 24 by 25. 24 by 25 times RH. But this is momentum of photon. You want velocity acquired by atom. Okay, so by law of conservation of momentum, what you can say is, by conservation of momentum, what you can say, the momentum of photon plus momentum of atom. Okay, momentum of atom plus momentum of photon is equal to 0. Right, so momentum of atom, let's say mass times velocity of atom, ma times va, plus momentum of photon is p, and that's equal to 0. Move that p on other side. So what was p? P was 24 by 25 times RH. Let's move it on other side. So you get ma times va is equal to minus 24 by 25 times RH. But this negative sign just tells that the atom moves in other direction, right? So then just move mass of atom on that side. Mass of atom is m, so you get velocity of atom is equal to minus 24 by 25, and m will go in denominator, mass of atom, or they are calling it as m only, so let's call it as m only, right? So velocity of atom would be minus 24 by 25 times RH by m. This would be the answer. Okay, so it is option A, RH, HR by m, right? 24 by 25 HR by m. Okay, is this question clear? Okay, everyone? Yes, no? Okay, good. This was by far the best question, I can say. Spectral line, this question is also good. Okay, good meaning it requires some thinking to solve, right? Other questions are like just plug and play. Most of the questions, plug the formula and get the answers. Now, most of them are no, these questions are also good, but they are lengthy. Anyways, let's come back. Let's see this question. The transition from state n equal to 3 to n equal to 1 in a hydrogen-like atom results in ultraviolet radiation. So n equal to 3 to n equal to 1. Transition is ultraviolet. The infrared radiation will be obtained in the transition from. Tell me, where can you guarantee the infrared radiation? 4 to 3. Very good. So this is you just need to remember, like Lyman is what? Transition from any nth level to first level, okay, and it lies in the ultraviolet region, okay. So this is Lyman series. This is first wavelength of Lyman series. This is Lyman series. And Lyman is ultraviolet. If Lyman is ultraviolet, then Balmer would be visible. And next to that, Paschen, okay, that is transition to third state from any higher state, right? Paschen, bracket and P and etc. would be infrared. So very good, that's correct. So 4 to 3, right? Others, is it clear? Okay, good. Let's see next one. Ionization energy of electron in hydrogen atom in the ground state is 13.6 electron volts. The atoms are excited to higher energy levels to emit 6 wavelengths. Okay, the maximum wavelength of emitted radiation corresponds to the transition between. Okay, so you just need to find out which is the maximum wavelength. Actually, ideally you will need to find out where does the electron go, right? You will need to find it out because it's emitting 6 spectral lines. So what is the excited level? Let excited level is n is the excited level, or excited state, right? Means number of the excited orbit. So then you have number of spectral lines is equal to what? N times n minus 1 divided by 2, and this is given to be equal to 6, right? So 6 is equal to n times n minus 1 divided by 2. So 6 times 2 is 12. So 12 is equal to n square minus n, and then you will need to find out the solution for this quadratic equation. Okay, n square minus n plus 12 is equal to 0. Right? So then what's the solution? It's minus b plus minus square root of b square minus 4ac upon 2a. Right, so minus b is minus of minus 1, so that's plus 1 plus minus square root of b square is 1 minus 4ac 4. Oh, this will be plus minus 12, no? Okay, this 12 goes on that side, it becomes minus 12. Okay, so 1 plus minus square root of 1 by 2, okay, b square is 1, and minus you have 4ac, 4 times of 1 into 12, okay, so minus 12 times, how much is it? Minus 12 times of 4, minus 48, and this negative sign, so plus 48, 1 plus 48, right? So that is 7, okay, 1 plus minus 7 divided by 2. So how much is that? So that is equal to 1 plus 7 by 2, that is 8 by 2 means 4. So n is equal to 4. Okay, you got n equals to 4, right? Okay, so to what excited level does the electron go? It goes to n equals to 4. Okay, solving this, right? And then if it goes to n equals to 4, the maximum wavelength of the radiation corresponds to the transition between. So maximum wavelength means the energy is minimum, so that is the nearest transition. So n equal to 4 to n equal to 2, sorry, n equal to 4 to n equal to 3. Which one? Tell me. This one would be maximum wavelength, right? Everyone? How come? Okay, first of all, uh, what should we do? Okay, why did I verify this? Because looking at these options, you can directly find out that maximum wavelength would be for the transition having minimum energy difference, that is n equal to 4 to n equal to 3. Okay, we'll see how. Okay, but then your electron should go to that nth level, otherwise they can write down anything. If they say if they say uh, in some option it's n equals to 8 to n equals to 7, then that would be your answer, right? So ideally you need to check this. Okay, all right, so let's see. So energy of the first orbit is what? Minus 13.6 electron volts. This is energy of first orbit or first level. Energy of the second level is how much? It's minus 3.4 electron volts. Okay, this is energy of second level. Okay, this is E2, this is E1, this is E2. Then what's E3? So E3 is minus, okay, it's minus 1.5. So E3 is minus 1.5. What's E4? E4 is equal to minus 0.85 electron volts. Okay, and suppose 0 is somewhere here. So that's 0, suppose this is 0. So now you can see the energy difference between, see, nearest orbits, energy difference between nearest states would be lesser if you go to higher and higher states. So what do I mean by that? Energy difference between first and second state, how much is it? So energy of the second state is E2 is equal to minus 3.4 electron volts. So this energy difference is equal to what? 10.2 electron volts, 13.6 and 3.4, right? But then when you go from second to third, the energy difference is, how much is the energy difference? It's 1.9, right? 3.4 minus 1.5 is 1.9. Okay, then you go from here to here, the energy difference decreases. Okay, so energy difference between the nearest levels will go on decreasing as you go to the higher and higher level, to higher and higher state. Is this thing clear? Everyone? Right? So energy difference between nearest state, so E2 minus E1 is equal to what? 10.2 eV. E3 minus E2 is equal to 1.9 eV. E4 minus E3, E4 minus E3 is equal to what? 0.75 or something like that. This is 0. It's 9, 0.65. Okay, so it would be 0.65 EV. Okay, so as you go to higher and higher level, what happens? The energy difference between the nearest levels, okay, it goes on decreasing. E4 minus E3 is less than E3 minus E2, and it is less than E2 minus E1, right? So this is observation, you need to remember it. Okay, and that's why if energy difference is minimum, then what would be the frequency difference would be minimum, and what would be the wavelength difference? Wavelength difference would be maximum. Right, or emitted wavelength would be maximum. Okay, so maximum wavelength of emitted radiation corresponds to the transition between what? N equal to 4 to n equal to 3 states. All right, this is clear, everyone? Okay, good. Now looking at the options only, what you can do is you can click this one, because energy difference would be minimum for this for sure, right? But then you need to check whether your electron goes to that level. In this, okay, this question setter is, she's honest, we can say, right? Because he's not giving any random options. Okay, what question setter can do is they can give this option, and they can give, let's say, n equals to 8 to n equals to 7, something like that. And we might feel, because we know this, that energy difference between higher orbits, nearest higher orbits, would be lesser, so we'll tend to click that answer, right? But that's not correct. Okay, that's why we need to check where does it go, right? Okay, let's see next one. Ionization potential of hydrogen atom is 13.6 eV. Hydrogen atoms in the ground state are excited by monochromatic radiation of photon energy 12.1 eV. According to Bohr's theory, the spectral line emitted by hydrogen will be. Okay, so we just need to check where does it go, right? Where does it go? So you have En minus E1 equals to energy of this photon, or the energy of nth orbit is equal to E1 plus energy of the photon. So En is E1 divided by n square, and that's equal to minus 13.6 plus 12.1. Okay, atoms are excited by the monochromatic radiation of 12.1 electron volt. Put that here. So this is equal to it's equal to what? Minus 1.5, right? Minus 1.5 electron volt. So this is third orbit. Okay, this is third orbit. You can check that by doing minus 13.6 divided by n square would be equal to minus 1.5, right? So take n square on this side, 1.5 on this side, but then dividing 13.6 by 1.5 will give you 9. Okay, but it's better to remember, as I said, first 4 energy levels. So this is the third orbit. Okay, so here n is equal to 3. We can get that from here. And if n is equal to 3, how many number of spectral lines are emitted? Tell me. It's n times n minus 1 divided by 2. That is 3 times 3 minus 1 means 2 upon 2 means 3. Okay, so 3 spectral lines would be emitted, right? This is clear. All right, good. Let's see next one. Energy levels A, B and C of a certain atom corresponding to increasing values of energy. EA is less than EB is less than EC. If lambda 1, lambda 2 and lambda 3 are wavelengths of radiations corresponding to the transition C to B, B to A and C to A respectively, which of the following relations is correct? EA, EB, EC and lambda 1, lambda 2, lambda 3 are wavelengths of transition from C to B. Okay, then C to B, lambda 1. Okay, B to A, lambda 2 and C to A, lambda 3. Right. So you want relation between these wavelengths. Suppose this is okay. So this is orbit A, this is B, this is C. Okay, state A, state B, state C. Right, they are in ascending order. Right, they are in ascending order. So A, B, C. Alright, so when electron jumps from C to B, that's not given. It jumps from C to B. Yeah, C to B, the wavelength would be lambda 1. Okay, when electron jumps from here to here, the wavelength of emitted photon would be lambda 1. That's given. When it jumps from here to here, it is lambda 2, and when it jumps from here to here, it's lambda 3. That's given. So the relation between lambda 1, lambda 2, lambda 3, that's very simple, right? That is very simple. You know this that okay, this energy difference can be written as energy difference between C and A can be written as energy difference between C and B plus energy difference between B and A, right? So what you can say is energy of C minus energy of A is equal to energy of C minus energy of B plus energy of B minus energy of A, energy of B minus energy of A. Okay, so that's simple. And when electron jumps from C to A, it emits a photon of energy equal to what? Energy difference between these two levels. Okay, and wavelength of that photon is equal to lambda 3. So what you can write, energy difference between these levels is equal to energy of the photon having wavelength lambda 3. So that is hc by lambda 3. So you have hc by lambda 3 equals to, when it jumps from C to B, it emits a photon, C to B emits a photon of wavelength lambda 1. Okay, so hc by lambda 1 plus when it goes from B to A, it emits a photon of the energy of hc by lambda 2, right? So hc would get cancelled. So 1 by lambda 3 is equal to, you have 1 by lambda 1 plus 1 by lambda 2. Okay, so 1 by lambda 3 is equal to 1 by lambda 1 plus 1 by lambda 2. So then you just need to rearrange this and you will get the answer. Okay. So you have 1 by lambda 3 is equal to 1 by lambda 1 plus 1 by lambda 2. So that's equal to, just do cross multiplication. So this would be equal to what? Lambda 2 divided by lambda 1 lambda 2, right? And this would be equal to lambda 1 times divided by lambda 1 lambda 2. Okay, so this is lambda 2 plus lambda 1 divided by, you have lambda 1 plus lambda 2. This is 1 by lambda 3, and therefore, oh, I wrote plus here. Okay, so therefore lambda 3 would be equal to what? Lambda 1 lambda 2, take reciprocal, divided by lambda 1 plus lambda 2. Lambda 1 lambda 2 divided by lambda 1 plus lambda 2. So it's option B. Okay, this one is clear. Right? Okay, very good. So this is repeated twice. Let's see next one. Maximum frequency of emission is obtained for the transition. This is very simple, tell me. Yes, 2 to 1 or 1 to 2, 2 to 6. Option B, 6 to 2. You think it is 6 to 2? Actually, the answer would be 2 to 1. See, why is it so? The reason is, what would be the energy difference between the second and first orbit? So see, the difference in energy, sorry, E1, this is E1, okay, this is minus 13, this is minus 13.6, and this is minus 3.4 electron volt. Okay, so energies of next orbits are even lesser in negative values than the energy difference between these two, right? So see, what's E2 minus E1? E2 minus E1 is 10.2. 10.2 electron volts, right? Minus 13.6 minus minus 3.4 minus 13.6. Okay, so this is 10.2 electron volts. Now you take any level, its energy would be less than what? Minus 3.4, right? But it will be less than meaning in negative values less than, actually the energy would be greater because it is less in negative values. Okay, but magnitude wise, so what would be energy of the sixth level? If you think about this one, energy of sixth level, so E6 is E1 by 36 minus 13.6 divided by 36. So nearly I can say it is 0.3. Okay, roughly 0.3 minus 0.3 EV, right? 12 3s are 36. Okay, so roughly 0.3, and that's why what would be the energy difference between these two? So it's 3.4 minus 0.3, right? So that is 3.1 EV. Okay, so energy difference between these two is much greater compared to energy difference between any of the next orbits. Okay, so that's why the answer is 2 to 1. Okay, so if energy difference is greater, the frequency of the emitted photon would be greater. This is clear, everyone? Others? Okay, good. All right. Okay, so always think in this way, right? Okay, let's see next one. When an electron does transition from n equal to 4 to n equal to 2, emitted line spectrum will be. This is very simple question, but they have asked it at some point. Okay, so what is this? It is jumping to n equal to 2 means it is Balmer series, and it is jumping from 4. If it jumps from third to second, that's first line. If it jumps from fourth to second, it is the second line. So it's second line of the Balmer series, right? It is second line of the Balmer series. Okay, that's very simple. Okay, let's see next question. Consider an electron in the nth orbit of hydrogen atom in Bohr model. The circumference of orbit can be expressed in terms of de Broglie wavelength, lambda of electron as. Tell me. So this is simple. So we had seen this, that where does the second Bohr's postulate come from? So if you think of electrons as the matter waves, so because it is moving in a closed path, the matter waves associated with electron will be stationary waves. They will be what? Stationary waves. Okay, so here stationary waves will be formed. So distance covered in round trip for the stationary waves must be equal to what? Must be okay, something like this. Okay, these are loops, right? These are loops. So one loop is equal to what? Lambda by 2, and therefore there might be n loops. Okay, there might be n loops, right? So 2 pi r must be equal to what? N times of lambda. Okay, 2 pi r must be equal to n times of lambda because it is distance covered by wave in a round trip, so that's equal to n times lambda, right? So that's the answer. It's option D. This is clear, everyone? Okay, yes, Nikita, is it clear? All right, so this is just de Broglie's explanation of Bohr's second postulate. Okay. All right, good. Let's see next one. Out of the following, which one is not possible energy for a photon to be emitted by hydrogen atom according to Bohr's atomic model? Tell me. So this question you need to solve by trial and error. Okay, there is no other option. So E1 is equal to, you have minus 13.6 electron volts, right? And if electron jumps from infinite orbit to the ground level, that means a free electron jumps to the ground level, then this much energy would be emitted. So this is completely fine. Okay, it will emit 13.6, a photon of energy, 13.6 electron volts. Okay, so it's like a free electron is captured by a proton, right? So hydrogen atom would be formed in that case. Free electron is captured by a proton. Okay, so a proton captures an electron, means what? A hydrogen atom is formed. Okay, so in that case, what was the energy of free electron? It was 0. And what is the energy of the hydrogen atom first orbit? Minus 13.6. So if energy of electron becomes minus 13.6 from 0, that means it has lost energy equal to 13.6, right? So that is possible. Next, we need to check the others. So E2 is equal to, minus 3.4 electron volts. E3 is equal to minus 1.5 electron volts. E4 is equal to minus 0.85 electron volts, 85 electron volts. So now take the difference. Is it near to these values? So 0.65. Do you get 0.65? So I guess E3 and E4, if you take difference, we had seen this in one of the questions, that E3 minus E4 minus E3 would be equal to 0.65, right? Okay, so minus 0.85 plus 1.5, 1.5 minus 0.85 is 0.65. That is also possible. 1.9, is it possible? You can check difference between these two is 10.2. Difference between these two is indeed 1.9. Okay, so E3 minus E2 is equal to 1.9, right? Because this is minus 1.5 and minus minus plus 3.4. So 3.4 minus 1.5 is 1.9, and that's why this is the answer. Sorry, this is also possible. This is also possible, sorry. So what is left? 11.1 electron volt is left. That's why this would be the answer, right? All right, so this is atoms. Tomorrow we'll start with the next chapter, that is nuclei, right? And nuclei is cut down like anything, so most probably we'll complete it tomorrow only, because they have removed, there were topics called as isotopes, isotones, isobars. They have removed it. Then there was a topic called as nuclear fusion, fission, etc. Okay, radioactivity was there. Okay, so most of the topics they have removed. Anyways, so let's stop here. See you tomorrow, and please try to solve the questions based on atoms. Okay, all right, bye.